Okay, this is section 6.1. We're trying to shed light on the quadratic form thing. I know I got technical there. And so in matrix terms, we had a x transpose a x like that, and what this turned into was a x squared plus 2h xy plus by squared, and then we set that equal to some c. And as I pointed out, this makes various conic sections, and so you could get a circle, you could get an ellipse, you could get hyperbola, parabola out of this form. And so a little bit on why we like this form to actually not have that middle term. So if we start with a circle, right? I know the area of this circle, if this is r here, the area is pi r squared. And then if I wanted a particular section of that, so I'm going to draw all these this way. Here's a theta 1, here's a theta 2, and so the overall theta of this section is theta equals theta 1 minus theta 2, because theta 2 would be a negative angle going from the x-axis. But as you look at this, right, well, that's just some proportion of a circle. Well, what proportion is it? Well, it's, in this case, a for this sub theta here, so a of theta, it is theta over 2 pi parts of that circle, so pi r squared. And so that gives us the basic formula of theta over 2, oops, no pi there, because that cancels. So a circle sector is, the area is theta over 2 r squared. So now if you go to an ellipse, and we'll draw it this way for right now. So we'll call this lambda 1 and this lambda 2 for the distance to these axes. Now, if I just want the area of this, actually a nifty little trick to get the formula is I can make this a circle by taking all the y values and multiplying by lambda 1 over lambda 2. See, so, you know, here's a given xy value in there that's on that ellipse. And if instead I take x and lambda 1 over lambda 2 times y, I end up with a circle. And so that's a you know, so, you know, if I did that, see, it would stretch the y here, and so I have that. Now let's look at what happens with some theta 1 and theta 2 in here. So I can still get a sector here, you know, so I have my theta is theta 1 minus theta 2. And now, though, I need to make a new theta because I've got that circle. So here I'm going to draw a circle, and this is a circle of radius lambda 1. And when I draw this new one up here, so I'll call it theta hat, there's a hat 1, and I get a new theta 2, so this is theta 2 hat. And of course this is lambda 1. So I got my theta hat, and that's theta 1 hat minus theta 2 hat. And I know it here, so if I take this sector, I already know the answer is A equals theta hat over 2 times r squared, but that's lambda 1 squared. And so now, though, if I what am I thinking here? Who knows what I'm thinking? So now, once I've found that area, I can go back. I need to squeeze everything back down by that same proportion. And so once I do that, I need my, so this is, I'll put a C for a circle, and then A for the proportion of the ellipse itself. I need to, remember I multiplied through by lambda 1 over lambda 2, so to undo that, I'm going to multiply lambda 2 over lambda 1 AC, and so what that gives me is theta hat over 2, and then I had theta lambda 1 squared, but I'm dividing by a lambda 1 and multiplying by a lambda 2, so I end up with a lambda 1 times lambda 2 here. And notice that if it's the whole circle, this becomes pi theta 1, or pi lambda 1 lambda 2, which is the area of a full ellipse. Okay, so this, now I have to talk a little bit about getting theta 1 and theta 1 hat and theta 2 hat, but other than that, this is pretty simple, right? If all I have to do is multiply through by that lambda 1 over lambda 2, and I don't actually have to do it in theory to get my answer, but you know, I multiply through by that to make that into a circle, get the answer for the circle, but of course that distorted these angles when I made it into a circle. So I do that and then just undo it, and I get this formula. Okay, so pretty straightforward. Now, the theta 1 hat and the theta 2 hat, notice you have that in the original, if we set this up, so I'm just going to look at theta 1. So here's theta 1, and so this was y and this was x. Then I multiplied y to get lambda 1 over lambda 2 y, like that, up here. And so, and then that, of course, is my theta 1 hat. So we see that the tangent of theta 1 hat is equal to, instead of y over x, it's equal to lambda 1 y over lambda 2x, if I write it that way. So theta 1 hat is the arctangent or inverse tangent of lambda 1 y over lambda 2x. So that's how I would find that, and then similarly I would do the same sort of thing with arctangent here, and I would have oh well, I better name that. I just called that y and x back here, but you know, I should probably think of that as a x1 y1 and then a x2 y2 down there. So I'll call that x1 and that x1, or y1 and x1, and there's a 1 and a 1 and a 1 and a 1, and then similarly I would have lambda 1 y2 over lambda 2 x2 like that. And so that's how I would get those. And so that's not so bad. I mean, we can find these arctangents and so forth. So putting it all together, the area of that sector of the ellipse is lambda 2 over lambda 1. Well, let's see. So actually, let me go here to the lambda 1, lambda 2. So it's lambda 1, lambda 2 over 2, and then times my arctan of lambda 1, y1 over lambda 2, x1 minus the arctan of lambda 1, y2, lambda 2, x2. So, you know, it's not the prettiest formula, but in the end, not bad. You know, so if I know that length, that lambda 1 and lambda 2, and I know the x's of my that create this sector that I want, I can get that answer. Okay, so that is finding the area of a sector of an ellipse. And you know, so the idea here, we're looking at this motivation a little deeper than they give us to see what's going on. Another reason is, actually, this is something I'm very interested in, is areas and volumes of ellipses and ellipsoids, or parts of ellipses and ellipsoids. And so, again, if the ellipse is nicely oriented, I can get that answer very easily. Okay, you know, so something like this. But the problem is now, you know, if that ellipse is doing that, now it is not so easy to do. Now, in one way, you could say, well, sure, it's still easy, because, you know, if I have, you know, these things and all that, I can just use this formula. Well, not exactly, you know, because typically the way, you know, if you truly gave me this theta 1 and this theta 2, yeah, I'd be all set. I could do it. But I still need that theta 1 and that theta 2. And likely you don't have those. Okay. What you probably have are more things in symbols and numbers and all that in this form. And so if you think of trying to automate this process, yeah, I'm still going to have problems. Now, you know, again, if I just know the theta 1 and theta 2, piece of cake, but that's the whole point, is, well, I probably don't know theta 1 and theta 2 right off. You know, for instance, let me redraw this and, you know, have it there. Suppose I want the area in this quadrant here, you know, in the positive quadrant, then you know, I would need to know that line, right? I would need to know that angle in order to tell you what theta 1 and theta 2 were. And so again, there's kind of the problem is we have to find a way to figure out that angle. Okay, so it could be this is theta 2 and that's theta 1, and in this picture, oh yeah, okay, piece of cake, I get it, the two of them add up to 90 degrees, but it does matter. It's not just the angle itself with an ellipse, right? It matters where that angle is, because here this same sector here with theta 1 and theta 2, it's going to give me a very different answer than if I took that sector over here somewhere, right? Because the ellipse is longer, there's going to be more area. And so, when I say I know, if I just know theta 1 and theta 2, then I'm all set. Well, but that's the problem, is likely you know everything in terms of coordinates, and therefore you have some work to do to try to figure out theta 1 and theta 2. So even here, in this case, I have some work to try to figure out what theta 1 and theta 2 are, because, well, I don't necessarily know what that line is. And so that's the question. Can I find that line? Can I figure out what the correct theta is between, if I call this the x1 axis again and this the y1 axis, then can I find that theta? Sorry about that. Can I find that theta for the difference in those two axis systems? So that's the thing. That's the motivation. Is that I need a way to take a look at my ellipse in the form a x squared plus 2hxy plus by squared equals c. I need to find a way to figure out how this is oriented on my usual xy coordinate system, so that then I can figure out what the new axes are, x1 and y1. Okay, so that's the deal. That's why we're interested in pursuing this problem.